Hi, my name is Michael Ostroff, and I'm a PhD student at FAU. I would like to talk to you about how dark matter might work in my dimensional collapsar theory. I say might because I don't actually know if this will work. It's more of a hunch than anything, I suppose. Anyways, so, and because my theory is essentially like higher dimensional like vacuum GR, which is like Kaluza-Klein theory, all particles in it have to have like they can't have any like gravitational singularities where the curvature goes to infinity, and these kinds of structures are referred to as Kaluza-Klein solitons, and in order for them to like not have these singularities, they also need to have this property which is known as zero gravitational mass. And this is like a very counterintuitive thing if you think about it, because if you had a Kaluza-Klein soliton right here and you had a test particle which was moving through the 5-dimensional space-time in a purely time-like trajectory, then it would have to not like curve towards the actual Kaluza-Klein soliton. It would have to just keep moving forward. And this is kind of counterintuitive because if you imagine like a body in like 4D space-time and a time-like trajectory, then this trajectory would curve into the gravitational well of this planet, and that's how you would think it like should work. However, geodesics and like get a bit different when you go from like 4D to 5D with a compact space. So there could be there's some like stuff that which could like change things essentially. You see, motion through the compact space, like the one sphere, actually any compact space in general, is essentially associated with like a test particle having a certain like charge essentially. And for like the one sphere, which is a compact space in Kaluza-Klein theory, that's associated with like either like a positive or negative charge. And this isn't like related to your motion through the like compact space. So like being still in the compact space doesn't mean you have like zero electric charge essentially. It's a bit more complicated than that. So there's also this thing called the river model of general relativity, and like this is kind of rooted in the idea of the Ricci tensor. So in the vacuum, like a dust cloud, like the Ricci tensor vanishes and a dust cloud will like maintain constant hypervolume. However, if in that dust cloud there's like some matter or energy, it can cause that dust cloud to like contract over time. So if you were there's like this like river model of general relativity, basically in it matter and energy are just sucking in space-time. So if you had like a dust cloud which was around the Earth, it would essentially get sucked into the matter. But if it were to not be around the Earth but maybe like falling towards it, then it would just get distorted by like tidal forces, but its hypervolume would actually still stay constant. So in order for like this to essentially work out in Kaluza-Klein theory, you can't have like this dust cloud which is surrounding the Earth. It can't actually be getting reduced in hypervolume. Its hypervolume needs to actually stay the same. And the way I think that this works is, I think these Kaluza-Klein solitons are acting as these like sorts of dimensional expandars. So dimensional collapsars basically take a compact space and shrink it in order to expand the extended dimensions even more. However, these Kaluza-Klein solitons, they'll have an associated, they'll have a scaling compact space associated with them, and what I think that they do is that they suck in extended space-time, like massive bodies in like the river model of general relativity, and I think it expels all that space-time into the compact space, causing it to essentially bulge outwards and become larger in the vicinity of like massive particles. So if you were to have a Kaluza-Klein soliton here, then it would be sucking in the extended spacetime while also expelling said spacetime in the compact space. And this would cause the dilaton field, i.e. like the size of the compact space, to essentially bulge around these particles. And I think that these like this scaling compact space, like the one sphere in the case of our universe, determines the size of these particles. And because this caused this, like the dilaton field essentially bulges around like particles, it should essentially mean that if you had a bunch of particles all together in one space, then all this like this like because okay, so all this like dimensional expansion of like the one space of the one sphere should essentially like combine together. And if you had something like a galaxy, the dilaton field would like bulge outwards like relatively a lot around it. And I think it's that this like variation in the size of the compact space, I think it might be responsible for what we generally consider gravity to be. So essentially, like the size of like a particle essentially determines how fast like time passes for it. Because you could imagine you can imagine building a photon clock out of particles, where a photon essentially bounces back and forth between 2 points. However, if this photon clock were to be like twice as big, it would take twice as long for this photon to essentially bounce like back and forth. So the larger the particles are, the slower the time passes for them. So I think as like particles like move into a region where the dilaton field bulges outward and it's larger, they're going to grow in essentially space and time. And because like the scaling compact space like sets the scale of them, and they'll actually like experience like time passing slower and like deeper inside the gravitational well. And I think that there's a common interpretation of how gravity works, where like time dilation is essentially the cause of gravity, and essentially this is like I think kind of how gravity might work in dimensional collapsar theory. So this is a bit like different from how we like normally think of gravity, and it has some like interesting effects. So because it's I think there should be some like a wave-like element to this dilaton field. So in theory, you should be able to have these things called like dimensional waves, which are waves in the size of the compact space in like Kaluza-Klein theory. And I actually did a project on this like during the 2024 Wolfram Winter School. I did a project on like dimensional waves and was like analyzing how they essentially worked. And that's kind of when I realized that they might have the ability to alter the size of like particles and stuff. So this is leading to the second point. So imagine you have two galaxies and they're hurtling towards each other. They both have these like dilaton fields, which are like bulging outwards like around them, which I will now refer to as like their dilaton halos. And when they go and collide, their mass will like hit each other, and most of the mass will stay in the middle. While the dilaton halos, because they're actually kind of like these gravitational wave-like structures, they'll just keep going without the matter which was like generating them. And as they move further away from the matter that was generating them, they'll eventually start to go and decay over time. And like the dilaton halos and their like gravitational effects will get weaker and weaker as time goes on. Meanwhile, the matter which was generating those halos will generate a new dilaton halo at the center. So if you were to look at the bullet cluster over time, I think you would observe the following happening. You'd have the initial collision, and when they collide, all the matter is essentially in the center and like all the gravitational field. Then you have the dilaton halos, which I think is like essentially kind of like dark matter in this case. Those like keep moving outwards, but over time they decay and like weaken until they're basically nothing. And then you have like a new dilaton halo being regenerated in the center where all the matter is currently. That's my guess how things should work. We could probably find like you could probably do simulations to figure out what the actual like qualitative or quantitative predictions for this are, but I have yet to do so, so I'm not 100% sure. Also, this also hinges on the idea that the size of the scaling compact space sets the size of particles. But if you remember, I kind of discovered this weird feature of general relativity like vacuum GR, which I refer to as like metric ambiguity, which kind of throws the whole concept of like time and distance like as determined by the metric tensor out the window. So I don't actually know what causes those, so I'm less certain of like this explanation than I used to be. And I'd kind of have to figure out how like time and distance actually works in general relativity first, or vacuum GR, in order to have any confidence that this is actually still correct. So yeah. I would also like to talk about a potential way you could test for or probe for the existence of a like one sphere compact space in our current universe using a tabletop setup. I am not entirely sure how sensitive this setup would have to be, because again, I don't have simulation capacity for GR yet, so I haven't been able to run like simulations to test this out. But essentially, there's this thing called the gravitational memory effect. And if you have like two black holes spiraling together and then they go and like merge, they'll emit a bunch of like gravitational waves and they'll travel outwards into space-time. And when they're traveling through a region of space-time, if you had like let's say a sphere of dust, it would get distorted by these gravitational waves as they like passed by, and it would like become like ellipsoidal in like different ways. But after it's done passing by, it would remain slightly distorted, like slightly ellipsoidal still. And essentially this like remaining distortion from the passage of these gravitational waves, that's known as the gravitational memory effect, and it emerges from like the nonlinearities in like general relativity. So in Kaluza-Klein theory, electromagnetic waves are actually just another type of gravitational waves. So in theory, they should also be capable of generating this like gravitational memory effect. So I speculate that if you were to have a like laser beam, which was creating a non-sinusoidal electromagnetic wave, not entirely sure what the optimal shape is because I haven't been able to simulate it, but if you had a laser beam that was strong enough in generating these waves, it should generate some anomalous electromagnetic field around the beam. And like with like conventional electromagnetism, you wouldn't expect this to happen, but with like if you was like 5D Kaluza-Klein theory, you would expect something like this to occur. And depending on how strong this effect is, you might be able to detect it, potentially using a bunch of like correlations over time, depending on how strong or weak the effect is. I mean, normally gravitational waves are like fairly weak, but considering we can like build our own like gravitational wave generator, i.e. a laser, and make it however strong that we want, it's possible that like that weakness, which is normally inherent in gravitational waves, might not be an issue in this case. Also, considering the phenomenon that you'd be trying to detect would essentially be electromagnetic in like nature, not like small variance in like the if distance between particles, it might be a lot easier to detect as well. So it's possible you could build a tabletop setup using some lasers and detectors, which could probe whether the electromagnetic field is caused by a one sphere compact space. Next year, I'm going to be doing a fair bit of work on complex systems research regarding like that fractal phenomenon of fractal flow I discovered in other compact spaces as well. And hopefully I can understand how integrable systems work better and maybe experiment with creating some and seeing how they behave, because they have a lot of interesting soliton like behaviors. So that's what I'll be up to next year. That's it for the physics stuff today. Be sure to check out my Substack and YouTube channel, and also check out my project on dimensional waves, which I did at the Wolfram Winter School. So yeah, that's it for today, and have a good day.